Hi, welcome back to the channel. So this is the first of project videos and I hope you like it. The project we're talking about here is called Backtest and this is a financial investment simulator. So quick agenda for this video. We are going to start with a quick introduction to the project. We're going to talk about the elements of financial systems that we are modelling and also which ones we're not. We're going to talk about the investment strategies that we are intending to test using the model. We're going to look at some code, we're going to look at the first results, and then we're going to take a look at the next steps for the project. So a quick introduction. A backtest program basically takes an investment idea and lets you run it against real stock market data. And we're going to give a strategy and amount of cash and let the algorithm decide which shares to buy, which to sell, when, and then we will graph the value of the portfolio over time. Now the data we're using is not good enough to make real investment decisions with this. That's not the idea here. The idea is simply to get an understanding of the algorithms, to learn about how these things work, what doesn't, and find the little kind of details and edge cases that you wouldn't necessarily find just by reading about this stuff. So what elements are we going to include? So we are including stock prices, the ability to have long positions, and not implemented yet but in the near future, short positions. Might include futures at some point. There are some interesting things you can do with futures, for example arbitraging synthetic shares against real ones, but those techniques tend to rely more on speed of execution, so I'm not sure how interesting that will be for this project, but I might look at it if I get time and decide that it is interesting enough. Things that we're not including: market cap data. Interlacing that with the price data would be more effort than we would gain for the project. We can do the project perfectly well without it. We're not going to model the bid-ask spread. We're going to assume that you can buy any sized order of any stocks at the opening price of any given day. We're not going to include taxes or fees, so the results of any strategy will naturally be biased to be better than they would in the real world. We're not going to include dividends, splits, that kind of thing. Just, again, complicated to work all that data in and doesn't really add to the underlying premise of what we're trying to achieve here. And we're not going to touch anything like mortgage-backed securities, complex derivatives, things like that. That's just out of scope. So what strategies are we going to look at? Well, first strategy we're going to look at is an index strategy. Basically buy the top end shares and rebalance at a fixed period over the life of the data we have. This should hopefully give us a good baseline to compare other strategies against, to know whether our other strategies are worth pursuing. Next strategy we'll look at is momentum investing. So simple idea is you find shares that are going up very strongly and invest in them, or shares that are going down very strongly and you short them. And we're going to look at mean reversion. So the basic concept of mean reversion is to find the mean value of a stock, and if the stock is away from the mean, either long or short the stock so that you will make money when it returns to the mean on the assumption that it will. Now it's not quite as simple as finding a mean price because the market as a whole moves over time, so you have to find a trend and use that to calculate an expected mean in the future. Then we're going to add a bit of complexity to that with market neutral mean reversion. So here, instead of finding an expected mean of a stock, you find two stocks whose prices correlate. You wait for them to deviate from that correlation and then you short one and buy another, and buy the other, such that when they return to the mean you make money. This has the advantage that if the whole market moves up or down, you still win. And then we're going to look at kernel methods, and kernel methods are a way of finding patterns in very high dimensional spaces by working implicitly in those high dimensional spaces whilst implementing in a lower dimensional space. Most common method is support vector machines, and so some funds claim to have had very good successes with these, so we're going to find out if we can. And finally, LLMs. There are people starting to claim that they are using LLMs, in some cases claiming they're using ChatGPT to predict market prices. I'm a little skeptical about that, but it will be interesting to delve into it and see what we can achieve. So let's look at some code. Here we are in Visual Studio. We have a test suite here. It's not massive, but neither is the code base so far. And one interesting thing to note is that we have a failing test. This has been failing since I wrote it. Basically what's going on there is the main window view model is very stateful. I'm not very happy with the way it works, and tricking it into actually running the thing we want to test is surprisingly difficult. That's a prime candidate for a refactor in the near future, so I have left that test for the time being. So in terms of how the code works, we are a WPF application using Oxyplot to do some charting in the main window. That's about as UI as it gets for the time being, and we are using the main window code behind as a kind of dependency injection composition route. So I'm not a massive fan of DI containers for complex applications. If your application's object graph is fairly simple, I think it's fine, but if it is complicated in any particular way, I don't like not being able to see how the code is structured. So what we have is a data source which loads in our market data. We have a class that provides the data, and we have another class called market at time, which I'll talk about in a minute. We have just some variables for starting capital and the company count in our index. That probably needs to move somewhere else eventually. But that will be moot because of future refactorings that I will talk about in the next step section. And then we have the data context, which is a main window view model, and this just takes the market data and a list of iPrice series. So an iPrice series is anything that can generate a series of prices over time. The view model will step that on a day-by-day basis and then graph those prices on a daily basis. Nothing interesting in the view model part particularly. So first thing we'll look at very quickly is the market data class. So we have an interface for iMarket data. It has the start and end dates, so when our data runs from, when it runs to. We have a list of companies. So this is a technique I use quite a lot, is to create simple types. So a company name is just a string, but because it's wrapped in a type, you can't accidentally pass something else that's a string. So like the name of a trader, for example, if we modelled that, you couldn't accidentally pass that instead of the name of a company. If you were passing raw strings, you could. I like carving up the problem space using types. It's one of my go-to strategies for making complicated problems manageable. And then the kind of key piece of all of this is the function getPriceAtTime. You give it a name and date, and it will return the price. And then in the implementation itself, we're not going to talk about it very much. We have some caching going on for the sake of performance. The only thing that's really worth talking about here is this where statement, which, as the comment mentions, is removing anything with any company which has a price at any point in time higher than $5,000 will be removed. Now this is because the data I'm using, there were quite a few companies within that had huge prices that then suddenly became very small prices. Now I think what's happening is there has been a shift from recording in basis points to dollars at some point in that company's history, or the market's history. Now if we were doing this for real, if we wanted to make investment decisions on this, you would have someone go through and sanitize that data by hand, you would process it algorithmically, you would do all sorts of things to get to salvage that data. Because we're not actually interested in making investment decisions, we're only looking at principles here, and this is not a massive part of the data set, we can just throw those companies' data away, which is what we do. The only downside to that is a few of the most valuable companies that have driven the markets over the past few decades also get thrown away, anything over 5,000, so probably Berkshire Hathaway, maybe Google's and Apple's and Microsoft's possibly. But again, not a problem for what we're doing. We are looking at average market data. I suppose that raises the question of why not just generate the data ourselves, and that would be a really, really bad idea. And the reason that would be a really, really bad idea is either you generate random data, at which point you're not going to be able to find any patterns in it, or you generate data with patterns in it, but then you know the patterns, and the whole point of this exercise is developing techniques that can find patterns. So you're kind of marking your own homework there, which is not good. So then the next interesting type to do with market data is market at time. So we have an interface iMarket at time, which just implements iMarket data, and then we have a market at time class, which has a date, and you can set the date, and then the get price at time function simply calls through to an underlying market's get price at time if the date that you want the price for is less than the current date of this object, and it throws an exception if not. And what this is doing, it's protecting us against accidentally looking into the future in our algorithms. It would be very easy to write an algorithm and make a mistake in some indexing or some date manipulation and end up reading data that we cannot possibly know yet, and that would be cheating. It would let us build algorithms that are impossibly good, and we could do that by accident. Now we could just have a market at time implement iMarket data and make sure we pass a market at time to a strategy, but again, you could accidentally pass the wrong thing, so this is free, it will be compiled out, so let's have the safety. So then if we go back to our main window view model, code behind, sorry, you can see the next thing we have that consumes all of this is a series of traders, and a trader is just an aggregate that gathers a portfolio and a strategy, and then when it gets updated every day, and it goes and generates an order and then executes the order. So portfolios are very simple, they're just a collection of cash and stocks, nothing worth looking at there really. And a strategy implements a strategy, so we'll look at that in a second. We won't actually look at the iStrategy interface, but we'll look at how it's used. So things worth noting when in the update function. So the first thing is how the strategy gets used. That was a bit quicker than I expected to get to it. So we have a switch statement based on the types of strategy. There is only one strategy now, and then we do something which will return an order. So an order is a list of trades that we want to run. Now, because we're going to have different types of strategy, we need to be able to call them in a generic way. And there's two ways really of doing this, and what we're looking at here is the less common approach, which is the more functional approach, where we're switching on type and using that to call a specific function. The other way we could have done this is to create a generate order function in the strategy interface and then just call that. And there's pros and cons to both approaches, and I have increasingly moved from the object-oriented interface-based approach over to the functional switch-based approach, and there's a couple of reasons for that. So the advantages of the object-oriented approach are that you have a fixed interface, obviously, but as in the function signature is fixed, you call it with the same arguments and you get the same thing back. And there's a lot of power in that standardization, and it makes it very easy to work with in certain ways. But then the other advantage, and the really big one, is that you could just call the interface function. You don't have to switch on the type, which means if you add a new strategy, then using that approach, the code will just keep working. Whereas if you had a new strategy with this approach, you will have to go and add a new element to the switch statement. And if you have lots of these switches throughout your code base, that's a lot of adding statements. On the other hand, the pros of the switch is that, well, it's the exact opposite, right? So you can have completely different function signatures, which gives you a lot more flexibility. You can make one strategy take one set of inputs and a different strategy take a completely different set of inputs if you need to, which, like I say, a lot more flexible. The other advantage, and the reason I use this a lot, and the reason I like it a lot, is that you can see all of the things that can happen right here at the call site. If you use the object-oriented approach, then you don't actually know, just by looking at the call, what set of strategies exists. You don't know what set of functions for strategies can be called, and you have to kind of go crawl across the code base to find them. And I really like having all of that visible right at the call site. It makes it a lot more explicit how you're using this to carve up the problem space, which is basically how we manage complexity, right? We break problem spaces down. That is how we do interesting things with code. So then the other two useful things to look at here, we calculate the values before and after. One useful thing, sorry, that's two code blocks, but it's doing one thing. And then we do a comparison to make sure that we haven't lost or gained money here. Now, this might seem a bit counterintuitive. We are trading to try and make money, so why do we need the price to be exactly the same before and after? And that's because we can only make money over time. This is a thing that happens instantaneously, and if the value of the portfolio before and after doesn't match, something has gone wrong. So this will catch errors in our code, because that shouldn't be possible. If it is, we have bugs. So that's all I really wanted to look at with the code. You should have a rough overview of how the program works and why it does the things it does. So now I'm going to jump back to our presentation. So let's look at some results. So this graph here is the result of running my initial index strategy over a period from the rough 2006 to 2017. And as you can see, we did not make a lot of money except on the green line. Now the green line isn't actually a strategy. The green line is the result of summing the overall shares in the market. The other lines are taking our index strategy at various different rebalancing periods. So the reason it looks like this is there are many bugs. Most of those are now fixed and it looks much better, but that is the subject of the next video. What we're talking about in the results here is how unexpected some of these outcomes were. For example, the widespread was very unexpected. And what I learned from this is it's surprisingly hard to actually understand what you're expecting here, because this is a strategy that is not a real world strategy. There are index funds in the real world, but they don't work algorithmically. They have people very carefully select and execute trades, and the index is also very carefully selected. And so getting a baseline for whether this is actually working or not is surprisingly difficult. So how do you do that? Well, what I've been looking at is what would you expect the results to be. So something as we do know from the real world is that the rebalancing period should have some effect, but it should be relatively minor. This is not a minor effect, so there must be bugs in here. And indeed there were, because I went and found them. And the other thing I learned was that this way of working is not fast enough. So because the UI is in the same program, to go and explore some data in any way other than debugging you have to stop the program, write a change, and then run it again. And some of the runs take a lot of time. Initially, it was taking a few minutes per run, and then it got up to 20 minutes per run, and then one run took 37 minutes, and I decided it needed refactoring, and now it's back down to about 50 seconds. But that's still a long time to go and wait for a change if you're doing many changes to try and explore what's going on in the data. So, the result of that, we get to the next steps. And the two next steps, which should be obvious from what I was just saying, are to implement the index strategy properly, and I will do a video on that shortly, and to do a major refactor. So the plan for the major refactor is that we are going to move towards a Python interface. So the C# code will still exist, but the C# will be a backend. It will do maths and calculation, and it will expose most likely a REST API, and then a Python script will connect to it, run some things, and plot some data. And that means that when I want to explore some more data, I can leave the C# running, and I can just write another Python expression and get another line on the graph. And then the other major refactor is going to be to put a database on the back end, so that I'm not constantly loading the data. And because when I have an idea and then I stop the program and I change it to explore a new idea and then I run it again, I've lost the data from the old idea. I want to be able to compare them against each other, and just stashing everything in a database is going to make that very much easier. So next video will be about the index strategy, which is more or less finished. It just needs one, I believe, final bug fixing, and I'll do a video on that and post it up. And then the video after that will be about the major refactor. That will probably be a week or two away. So once again, thanks for watching. I hope you found something useful in all this rambling. That's an introduction to the Backtest project. It's been an interesting one. I've learned a lot, and I'm looking forward to carrying on with it.